Okay, this is the pre-calc first semester exam review. First problem gives us a rational function, wants us to find the domain algebraically, and then support your answer with a graph. So the domain of a function is always all real numbers except for places where we get zeros in the bottom of fractions or negatives underneath even roots. Those are things we really got to look out for. So in this one, we get all real numbers here except for -3. So I'm going to say x is all real numbers for the domain, except for x cannot be -3 and 1. Now in interval notation, that'd be all real numbers from -infinity all the way to -3, as well as -3 to 1, and then as well as 1 to positive infinity, not including -3 or 1. So that's the way we want to write our domain in interval notation. Now with a graph, we're going to use the graphing calculator and plug this function in. So we're going to do alpha y equals and do the fraction. It's just easier to keep it organized this way, and makes it easier not to make a mistake. And if you graph this, then you get a rational function. I need to change my window. In a standard viewing window, then it looks like this, where we can see there's vertical asymptotes at -3 and 1, which we know. So it is all real numbers except for -3 and 1, which is exactly what we've said here. Next problem is the same thing, only we want to factor the bottom first. And now we can see that the domain would be all real numbers from -infinity. We can't have 0 and 5. So all real numbers all the way up to 0, not including 0, and then from 0 to 5, not including 5, and then from 5 to infinity. That's our domain. Now it turns out if we look at this later, we learn that at 5 that's a vertical asymptote, at x equals 5, and then x equals 0 as a whole, because these factors cancel. But all we care about for the domain is that those two numbers can't be put into our function. So you guys can handle graphing that and double checking it, but that's the domain. Okay, next problem wants us to graph this function. You can even answer this question without graphing it, but if you do graph it, it looks like this. It does have non-removable discontinuity. What that means, we call that jump discontinuity because it jumps from -infinity all the way to positive infinity. Removable discontinuity would be a hole. This is definitely not a hole. This is a vertical asymptote. We know it's a vertical asymptote because those occur at zeros in the denominator that aren't factors that cancel. Factors that cancel would be a hole, and that would be removable. But vertical asymptotes are non-removable. Okay, the next one is the same question. This is a tricky one. I actually would have had to graph this one and see that there is jump discontinuity, therefore it's non-removable. So there's not a hole there, it's not removable. Okay, the next question wants to find horizontal and vertical asymptotes. So let's find the horizontal asymptotes and the vertical asymptotes. Now, I'm going to factor this. I usually try to factor it if I can. X minus 1 and x plus 1 in the bottom. And so therefore, the vertical asymptotes occur as zeros in the denominator. So those would be x equals 1 and x equals -1. Horizontal asymptotes, because the ratio or the exponent is the same in the bottom and the top, we have the same degree in the top and bottom. Therefore, we take the ratio of the leading coefficients, which is 1. So there's our horizontal and vertical asymptotes. And that information is right on the formula sheet, so make sure that you guys put this information on there if it's not something you have all memorized. Let me show it to you real quick. All of that's right here. So we just use the horizontal asymptote information. We have the number 1 here, and we use the vertical asymptote information. Okay, for the next problem, let's find the composition both ways of these. So let's do f of g of x first. What that means is we're going to take g, this function here, we're going to plug it in to the domain of f, so it's going to go right there. That becomes the square root of x plus 1 squared minus 2, which simplifies to x plus 1 minus 2, which just becomes x minus 1, if you simplify it all the way. There's our composition. Now we can talk about the domain. The domain of that would be, this one would be all real numbers, but we have to look at the function we're plugged in, which is g, and look for any restrictions from that. So we're looking at this function. The restrictions from that are x plus 1 has to be greater than or equal to 0, because we have the square root. We can't take the square root of a negative number. So if you move the 1 over, you get x has to be greater than -1, so therefore our domain is all real numbers that are greater than -1, which would be -1 to infinity, including -1. Now I know that's not the domain of the what looks like this linear function here, but it is the domain of the composition because we have to keep the restrictions from the function we're plugging in. So there's the domain for f of g of x. Now let's go the other way around and plug f of x into g. So this is going to go, this right here is going to go right in for that x. So it's going to be the square root of x squared minus 2 plus 1. Now some people like to put parentheses around that to, to make you aware that you're plugging that function in. There's f right there. But we can drop those parentheses now and make it x squared minus 1. And I can't simplify that really. So that's my function. Now, I have to look at restrictions from this. So I know that what's underneath there has to be greater than or equal to 0 because you can't have a negative underneath there. So if I solve this, I get square root both sides. This is a weird one. You get x can be all numbers greater than or equal to 1, or x is less than negative 1. You switch the inequality and switch the sign. So we would write that domain negative infinity all the way to negative 1, as well as positive 1 all the way to positive infinity. That's the domain. And you can double check that with your calculator. You'll see that if you graph this, all real numbers are available except for this little spot from negative 1 to 1, which is what we have here. Those points are undefined because they give us negative numbers underneath our radical. So there's the domain. Now we don't have to look at restrictions from f because there are none. So we only have to look in this case at restrictions of the final function, which in this case there's the domain. Let's just try one more, f of g of x. We're going to take g of x right here, we're going to plug it in right there. So if we do that, we get 1 over 2 times g of x. I'm going to try to simplify this a little bit. This is 1 over 2 divided by 3x. Instead of dividing by a fraction, I'm going to multiply by the reciprocal. So I'm going to change this into 3x over 2. Just move this up and flip it. So there's my function right there. Now there are no restrictions on this domain. So according to this, my domain would be all real numbers. That's just a line with a slope of 3 over 2. But I have to look at my original function g, and there is a restriction here. X can't be equal to 0. So I need to make sure that I keep that in mind. I'm going to say negative infinity all the way up to 0, as well as 0 all the way up to positive infinity, because I can't include 0. That's a restriction on the original function g that I'm using to plug in, therefore it's got to be a restriction on my composition. So there's my composition, and there's my domain. All right, next problem, let's go the other way around. G of f of x then. Let's take f of x and let's plug it right in there into g. So we get 1 over 3 times f of x, which is, in parentheses, 1 over 2x. So similar, this turns into 1 over 3 over 2x, and I'm going to move that up and multiply by the reciprocal. So I'm going to get 2x over 3 when I do that. That's my composition. Once again, I need to look at restrictions from the original function f of x, which in this case is the same thing, 0, gives you a 0 on the bottom. So I can't have 0. So make sure you write that in interval notation saying all real numbers except 0. Okay, the next problem wants us to find the formula for the inverse function and then give the domain, and including any restrictions inherited. This can be important. In these two problems it doesn't turn out to be very much, but it can be, and I'll show you what I mean. The best way to find the domain and range. So the domain and range of the original function here is all real numbers. So negative infinity to infinity for both the domain and range, because it's just a line. That means that when I find the inverse, I just switch the domain and range to find the domain and range of the inverse. So keep that in mind. That can be important, not in this problem because it doesn't matter, but for future problems. So let's switch x and y here to find the inverse function. We have this. We can add 6 to both sides, and we can divide by 3. So our inverse function y is x plus 6 divided by 3, and I'll call that inverse of x, f inverse of x. There's our inverse function. They want the new domain. It's the range of the original, so it's just negative infinity to infinity, and that turns out to match what we have here anyway. So that wasn't very tricky. But sometimes you'll find that the domain of what you think you would have for the inverse here doesn't match the range of the original function, in which case you need to take the range of the original function. And that's what they mean when they say any inherited restrictions from f. All right, so let's try this again then with this function. I'll always write down the domain and range of the original, or the range of the original, if you'd like. the domain is all real numbers. We can have negatives underneath odd roots, so we can have negative infinity to infinity there. And the range is also all real numbers here. You can graph this if you're not sure. And it does keep going up and down forever, so there's all real numbers. So that's going to be the domain of our inverse. Let's find it real quick by switching x and y. And solving for y. So we're going to cube both sides, and we're going to then subtract 5. So we get y equals x cubed minus 5, which I'm going to then switch that back to f inverse of x. And the domain is the range of our original, negative infinity to infinity. Next problem, which wants to know which function is the inverse. Well, to find inverse, we switch x and y and solve for y. So subtract 1 from both sides, and then take the cube root of both sides. That gives us our inverse function, cube root of x minus 1, which looks like it's a. Next problem, let's find the domain and range of these functions. Okay, so this one first, the domain, I know what's underneath. This radical has to be greater than or equal to 0 because it can't have negatives underneath the even root. So that's what I'm solving. I'm going to subtract 4 from both sides. Negative x squared equals negative 4. Get rid of the negatives. And, and then if I get rid of the negatives by dividing or multiplying through by negative 1, I do have to switch the sense of the inequality. And then when I take the square root of both sides, that gives me x is less than or equal to 2, or x is greater than or equal to negative 2, because I do have to take both, right? We take the plus and minus basically and switch the sense of the inequality. So there is our domain. Now I would write that as negative 2 to 2, including both. So technically this word should be and right here, not or, because we're talking about the intersection of these two. I usually kind of look at this as a number line, and what we're saying is we want all the numbers less than 2 but bigger than negative 2, so we're talking about the numbers in between, which is this right here. So there's our domain. We also want to find our range then. Range is a little trickier, but if this is our domain, you can plug these in. Imagine plugging both endpoints in. You'll find if you do that and plug in 2 squared, you get 0 both times. So 0 is one end of the range, and then to find the middle then would be the highest point or the lowest point. So plug in 0, which is the middle of this, and you get the square root of 4, which is 2, which is negative 2. So we're going between 0 and negative 2, so we would say negative 2 to 0 then, and we can have those endpoints as well. Now, it might be easier for you to graph that and see that on the graph from 0 to negative 2, which is also helpful to make sure you double check. Next problem, same thing. I want to find the domain and range. I'm going to factor this thing first, so I'm going to make it x over x times x minus 2. And so what we find is all real numbers except for 0 and 2. So I'd say negative infinity all the way up to 0, as well as 0 to 2, as well as 2 to positive infinity. That's all real numbers except for 0 and 2 for our domain. And then our range. We can get all real numbers out of this except for the horizontal asymptote, which in this case, since it's higher in the bottom than the top, the degree, y equals 0 is the horizontal asymptote. And you can see that from the graph as well. So what that means, we can get all real numbers except for that horizontal asymptote. So we'd say negative infinity all the way up to 0, not including 0, as well as 0 all the way up to positive infinity. That would be the domain and range. Now make sure that you're double checking this, with the graph and with your knowledge about the algebraic rules for domain and range, because if you look at this graph alone, you wouldn't see that this hole right here at 0. You'd say, okay, well, the domain's all real numbers except for 2, which we have 2, but it also can't have 0, and the reason it can't have 0 is because 0 on the bottom right here gives you 0 over 0, which is also undefined. So at 0, there is an undefined value right there. You can find it in your table if you go to second table, and you look at 0 right here, there's an error. So make sure you're double checking with what you know from both the graph and your knowledge of the algebraic rules.